Welcome back. Let's continue our talk on sampling distributions. We're going to go to section 7.3, which has to do with sample means. We've already learned about sample proportions. Now we're going to do similar things with sample means. So our goal today is to be able to describe a sampling distribution, specifically with means. All right. Now, the sampling distribution of the sample mean x bar describes the distribution of values taken from or by the sample mean in all possible samples of the same size from the same population. Okay? So the x bar we're finding for all possible samples of that size. So the mean of the random variable x is mu, and the standard deviation is sigma. Let's just recap. What is the mean of the standard deviation when you have multiple distributions? X plus x plus x plus x. So let's quick recall. If we did that, the mean would be the mean of all of them. Add it up. Okay? And those are all of the individual distributions. Okay? Now, standard deviation, similarly, we're not just going to add them all up. Remember, we are going to be doing the variance. So that's the standard deviation squared for each one added up. And then the square root of that. Okay? Now that's how we would find it. But what about the average of all of the means? So we have a whole bunch of means. How do you find the average of all those means? Well, let's think about it. If you take all of those, which is ultimately, we'll say 4 mu, we have 4 of them, so the mean of x, that would be equal to this divided by 4, because we want to get it the average. So divided by how many there are, divided by 4, that cancels out the 4s, and guess what? It's just mu. So note, the mean of all the x bars, so all the averages of all the samples, is going to be equal to the true population mean. We'll get to that in a second. Similarly, standard deviation. For the standard deviation, we can take that same idea, which ultimately is the square root of 4 variances, and we want to divide it by 4. Kind of like last time, if we want to get it all under the same square root, we kind of need to square the 4 to put that under a square root. So this would be the same thing as square root of 4 sigma squared divided by 16, or 4 squared. And now, because we did that, we can reduce. This cancels out. This just becomes 4. And ultimately, we can reduce this even farther, because that we can then separate it. That's squared over square root of 4, which in this case, we're using, oh, I'm supposed to switch colors. That's our n. And in this case, it would reduce to just 2. But in general, we can say the standard deviation of all of our x bars, or sampling distribution, or sample means, would be, these cancel out, so just sigma on top over the square root of n. Okay? So, to put that into a little more computer print here, suppose that x bar is the mean of a simple random sample of size n drawn from a large population with the mean mu and the standard deviation sigma. The mean of the sampling distribution, so again, all those possible samples of the same size, is mu. Okay, so we've got this. We just said that. The standard deviation is sigma over the square root of n. And note, just like we've been learning, you have to do every time, big star here, the standard deviation of the sampling distribution of x bar is that as long as the 10% condition is met. We must know independence before we do that. Okay? So again, a reminder of that 10% condition. So let's apply that here real quick. We got the number of movies viewed in the last year by students at a large high school. Now, it's worth noting a large high school, probably over 1,000. It's good to note that. Has a mean of 19.3 movies and a standard deviation of 15.8 movies. So a lot of spread there compared to the mean. Suppose we take a simple random sample of 100 students from this high school and calculate the mean a number of movies viewed by the members of the sample. Identify the mean of the sampling distribution. Okay? Well, the mean of x bar is going to be, of all the x bars, is going to be 19.3 movies. We said it should be the same as the population mean. So we're good to go there. Part B says calculate and interpret the standard deviation of the sampling distribution. Well, we said the standard deviation is equal to sigma divided by the square root of n. But let's not even do that yet. We need to first check for independence. It did not say anything about independence. We need to do that. Is the sample size of 100 less than 10% of all students at this large high school? If it says large, we can assume yes. Okay? So, we checked for independence. Now we want to actually find the standard deviation. And we had the sigma was 15.8. So it's 15.8 divided by the square root of, what was our n, 100? Which gets you 15.8 divided by 10, which is 1.58. Okay? So again, we went from a standard deviation of 15.8 from the population to a very much smaller standard deviation, much smaller spread when we take all these possible samples of size 100. Now, I want to quickly pause and interpret this. And I have that here. So, if, basically what this is saying is, if all possible, and this is the sampling distribution idea, if all possible samples of 100 students are taken, the mean number of movies viewed will typically vary by 1.58 movies from the mean of 19.3 movies. All right? Don't find that unless you know or can check for independence first. So, now we have described the mean and standard deviation of the sampling distribution of a sample mean, but not its shape. So that's because the shape of a sampling distribution depends on the shape of the population distribution. And this is worth noting. If we know the population distribution is approximately normal, then the sampling distribution of x bar will for sure be normal. Okay? Now I took a look at a quick visual, and I'll show you this with an example after this. But if you look, the purple is a population distribution. It's relatively normal, but it's very spread out. It seems more spread out than normal, a little bit lower. It has that sort of normal curve, just has higher spread. When we take a sampling distribution, we look for all these possible samples of the same size. It really hones in on that middle, and the spread decreases. The middle is going to be the same, but the spread decreases. So I want to show that with this example here. The heights of young women follow a normal distribution with mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. This is something that we could have answered back in chapter 2, where we first started talking about normal distributions. Because we know for all women it is a normal curve. The mean is 64.5 inches and a standard deviation of 2.5 inches. And we're just asked, what's the probability that a young woman would be taller than 66.5? So 66.5 inches here and higher. So this is just typical find your z-score. Okay, get 0.8. Go to your table. It's going to be 1 minus, or you can use symmetry, but the probability that z is greater than or equal to 0.8 is 21.2119. So 2119%, a 21.19% chance. But if we go a step further and say, find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches, now that's different. Okay, we can look at the sampling distribution, and we don't even know if it's normal yet. We'd have to check our large counts condition, or in this case, though, we can say the shape is normal because the population is normal. So if we know that, then we can actually go into this. This is a sampling distribution. Maybe note that this is a sampling distribution. So we're going to make our normal curve, but it's not going to have the same mean and standard deviation. The mean will be the same, but the standard deviation we said is sigma, which was the 2.5, divided by the square root of n, which is 10. Now we can answer the question. We can find, before I find that sigma, do we know, are they independent? Did it list that? I don't believe so. So check for independence as well. Is 10 less than or equal to 10% of all young women? Yes, there's a lot of young women out of there. There's more than 100. So we still need to state that. We still need to check that. Now we can go on and actually use that. So Z would be again, we're using 66.5. 66.5 minus 64.5 divided by this 2.5 over square root of 10. So this time I got a Z-score of 2.53, and then the probability that's higher than that is 0.0057. So we have more data collected. We can really hone in on that center, and it's less variability. So there's a less chance, went from 21.19% chance to a 0.057 because we have bigger sample size, not just our population data. So unfortunately, most population distributions are actually not normal, or maybe we just don't know the shape. Maybe that's more common. But I want you to notice something about these. So our parent population, we have a uniform, we have a skewed, this is like an extreme one, or I don't know if you can say bimodal maybe, but it's just really on the extremes. Your sample data could be anywhere, but your distribution of the means is going to gather around the true center because you're going to have multiple samples. So it might look like this, but then let's say you increase the n, it's really going to shrink down that variability. This, really honing in on those middles, the true middles. And that's the idea of this theorem that we're going to introduce now. It's called the central limit theorem. It says when you take a simple random sample size n from any population with mean of mu and finite standard deviation of sigma, the sampling distribution of the sample mean x bar will be approximately normal when n is large, and specifically when n is greater than or equal to 30. That is a cutoff. This is a very important thing in statistics. If we have simple random samples of size 30 or more, that makes it so that we can assume it will become approximately normal. It just is. Now it might be approximately normal when it's less than that, but if it's at least 30, it's going to be approximately normal. That's what the central limit theorem is telling us. Okay? So I want to jump to this. It says the distribution of the number of calories in one Christmas cookie 'tis the season, is highly skewed with a mean of 85 and a standard deviation of 14.3. It doesn't say which direction it's skewed, but it's highly skewed. So question 8 says find the probability of randomly selecting a Christmas cookie that has more than 120 calories. Can we do that? We can't use a normal curve, so don't just start drawing a normal curve. It is highly skewed. But if we slide down to question B, find the probability of randomly selecting 3 dozen cookies that have an average number of calories above 91, or even an average number that's more than 120, if we want to go back there, we can. Because 3 dozen is 36 cookies. 36 is greater than 30. So we can say approximately normal by the central limit theorem. Okay? Now we can go into our work and we can make a normal curve and we can assume that the mean in this case would be the same mean as the population, which was 85 calories. The standard deviation, before I do that, we want to check for independence. Doesn't say anything about independence. So is our selecting 3 dozen cookies that have an average number of that. I mean, this is just Christmas cookies. It doesn't say it's from any specific population. So is 36 less than 10% of all cookies? Absolutely. But we need to check that. These are the things that we need to check for. Once we have those things, there's a lot more we can do. So the sigma was 14.3, so it's going to be 14.3 divided by the square root of n, and the n was 36, which is 6. So what you can do then is you can actually look, okay, average calories above 90, 91. And again, we have a sampling distribution, so that's going to be really gathered around the mean. The z would be 91 minus 85, 85, divided by the square root of 36, divided by 14.3 over the square root of 36, which is 6. And then we can go from there. Using your calculator, using your z table, you probably get 2.52. And the probability that z is greater than that, well, it's not a real high probability. It's actually pretty low. And it's 0.0059. Is that the same one we had on the last example? Seems awful familiar to me, and I didn't realize that. It's very close, very similar. So there's a 0.59% chance that the average number of calories would be above 91. All right? And that's the idea of sample means that I wanted to get to today, where we have a formula for each. We have to be able to continue to check for normality and also check for independence. But we can apply a lot of things once we have those. And that's section 7.3a. See you next time.